Welcome! Today we'll explore an interesting problem titled Number 1229 Meeting Scheduler. This problem challenges us to find a common time slot for two participants based on their availability. It's a great exercise in problem solving and algorithm optimization. Let's dive into the details and work through the solution step by step. In this problem, we are tasked with finding a common time slot for two people to meet. Each person has their availability represented as a list of intervals. These intervals are provided as two separate 2D arrays, slots 1 and slots 2, where each interval specifies a start time and an end time. Our goal is to determine the earliest time slot that overlaps between the two schedules and is long enough to accommodate a given meeting duration. If such a slot exists, we return the start time and the end time of the meeting as a two-element list. If no such slot is found, we simply return an empty list. This problem requires us to carefully consider the input format, process the intervals effectively, and check for overlaps that meet the specified duration requirement. To better understand the problem, let's look at the first example. Here, slots 1 contains the intervals 10, 50, 60, 120, and 140, 210, while slots 2 contains 0, 15, and 60, 70. The required meeting duration is 8 minutes. To find a common time slot, we start by identifying overlapping intervals between slots 1 and slots 2. In this case, both schedules are available during the interval 60, 70. This overlap is 10 minutes long, which is sufficient for an 8-minute meeting. Therefore, the earliest valid time slot is 60, 68, and that becomes our output for this example. Now, let's examine another example. Here, slots 1 contains the intervals 10, 50, 60, 120, and 140, 210, while slots 2 contains 0, 15, and 20, 30. The required meeting duration is 12 minutes. As we analyze the intervals, we can see that there is no overlap between the two schedules that can accommodate a meeting of this length. Even though there are some overlaps, none of them meet the 12-minute requirement. As a result, the output for this example is an empty list, indicating no suitable time slot was found. Finally, let's look at one more example. Here, slots 1 contains the intervals 1, 10, and 15, 20, while slots 2 contains 5, 15, and 18, 25. The required meeting duration is 5 minutes. In this case, there is an overlap of 18, 20 between the two schedules. This overlap is exactly 5 minutes long, which satisfies the meeting duration requirement. The earliest valid time slot that fits the criteria is 18:23, where the meeting starts at 18 and ends at 23. This becomes our output. Now, it's important to note that the constraints of the problem require us to handle large inputs efficiently, sort the time slots if needed, and account for edge cases such as empty schedules or insufficient overlaps. By carefully addressing these considerations, we can ensure the solution works for all valid inputs. To solve the meeting scheduler problem, we first considered two main approaches. The brute force approach is straightforward. We iterate through every pair of time slots from slots 1 and slots 2 to check for overlaps. For two intervals, A1, B1, and A2, B2, an overlap exists if max, A1, A2, min, B1, B2. If an overlap is found, we calculate its duration and verify if it meets the required duration. If so, we return the interval, start plus duration. However, this method involves a nested loop, resulting in a time complexity of O(m*n), where m and n are the sizes of slots 1 and slots 2. While simple to implement, this approach is computationally expensive for large inputs and doesn't take advantage of the fact that the intervals are already sorted. To address these inefficiencies, we turn to an optimized approach using two pointers. By leveraging the sorted nature of the intervals, we can systematically find overlaps with significantly less computational overhead. Let's break down how this works. In the optimized two-pointer approach, the intervals in both slots 1 and slots 2 are first sorted by their start times. We then use two pointers, one for each list, to traverse the intervals. For each pair of intervals, we check for overlap. If there is an overlap, we calculate its duration. If the overlap duration meets or exceeds the required duration, we return the interval, start plus duration. If the overlap is insufficient, we move the pointer corresponding to the interval that ends earlier, as this ensures that we progress toward finding a valid overlap without missing any potential matches. This method is highly efficient because sorting the intervals allows us to avoid revisiting past intervals, reducing redundant calculations. The time complexity of this approach is O, m log m plus n log n, for sorting, followed by O, m plus n, for traversing the intervals. This makes it significantly faster than the brute force approach for large inputs. Sorting introduces some overhead, but this is negligible compared to the inefficiencies of nested loops in brute force. After analyzing both methods, we chose the optimized two-pointer approach for its efficiency and scalability. Sorting the intervals upfront ensures that we can systematically check for overlaps. The two-pointer traversal avoids redundant comparisons, making the solution robust even for large inputs. A key insight was recognizing that the sorted nature of the intervals allows us to prune unnecessary checks, which is a significant advantage over the brute force approach. By always advancing the pointer for the interval that ends earlier, we ensure steady progress toward a solution while maintaining correctness. Although the brute force approach might suffice for very small inputs, its O, m asterisk n, complexity makes it impractical at scale. In contrast, the two-pointer method's time complexity of O, m log m plus n log n, ensures faster performance and early termination when a valid interval is found. This trade-off makes the optimized approach not just more efficient, but also more versatile for a wide range of input sizes. The two-pointer approach provides the perfect balance of simplicity and efficiency, making it the ideal choice for solving this problem. It leverages the sorted nature of the intervals to minimize redundant computations and ensures scalability for large inputs. By combining systematic traversal with early termination upon finding a valid result, this method strikes a harmonious balance between performance and clarity, addressing the problem requirements in an optimal way. In this problem, we're tasked with finding the earliest time interval that can accommodate a meeting for two parties, given their respective availability slots and a required meeting duration. Each time slot is represented as a pair of start and end times, and if no common interval works, we return an empty list. To solve this efficiently, we first validate the inputs. If either of the availability lists is empty, or if the duration is less than or equal to 0, we can immediately return an empty list since no meeting can be scheduled. Next, we sort both lists of time slots by their start times. Sorting helps us align intervals in chronological order, which is crucial for an efficient comparison. The sorting step has a complexity of O, n log n, and it sets the stage for using a two-pointer technique. Once the lists are sorted, we initialize two pointers, one for each list. These pointers allow us to traverse the lists systematically, ensuring we can find overlaps without unnecessary comparisons. Now, we begin traversing the time slots using the two pointers. While both pointers are within the bounds of their respective lists, we look for overlaps between the current intervals. The start of the overlap is determined by taking the maximum of the two start times, and the end of the overlap is the minimum of the two end times. If the start of the overlap is earlier than the end, it means the intervals overlap. At this point, we check if the overlap duration is sufficient for the meeting. If the overlap satisfies the required duration, we return the start of the overlap along with the duration as the result. If not, we adjust the pointers. Specifically, we move the pointer corresponding to the interval that ends earlier. This ensures we efficiently move past intervals that can no longer contribute to a valid overlap. If we traverse through all intervals without finding a suitable meeting time, we return an empty list. There are several key insights that make this algorithm efficient. First, sorting the time slots ensures that intervals are ordered chronologically, which is essential for finding overlaps systematically. Second, the two-pointer technique is a critical optimization. Unlike a brute force approach that compares every pair of intervals, this method avoids unnecessary checks and reduces the complexity to linear traversal after sorting. The calculation of overlaps is another important insight. By taking the maximum of the two start times and the minimum of the two end times, we can quickly determine whether two intervals overlap and calculate the exact overlap window. Finally, the algorithm's efficiency is enhanced by always advancing the pointer of the interval that ends earlier. This ensures we minimize unnecessary comparisons and keep the traversal linear, making it well-suited for large input sizes. To implement this algorithm, we use a few simple data structures. The input lists of time slots are arrays of intervals, which we sort in place to avoid additional space overhead. We use two integer pointers to traverse the lists, which keeps the space complexity minimal. If a valid meeting interval is found, we store it in a single result list. From a complexity standpoint, the time complexity is dominated by the sorting step, which is O, n log n, for slots 1 and O, m log m, for slots 2. The traversal step is linear, O, n plus m, as we only iterate through each list once. Combining these, the total time complexity is O, n log n plus m log m. The space complexity is O1 for additional space, as the sorting is done in place, and we only use a few pointers and a result list. Finally, let's consider some edge cases. If there's no overlap between the two lists, the algorithm correctly returns an empty list because no meeting can be scheduled. If overlaps exist but are shorter than the required duration, those intervals are skipped, ensuring the result is valid. In cases where the two lists have identical intervals, the algorithm still works seamlessly by identifying overlaps and validating their duration. For large inputs, the algorithm remains efficient due to its O, n log n, complexity for sorting and O, n plus m, for traversal. These considerations make the solution robust and capable of handling a wide range of scenarios effectively. This implementation solves the LeetCode problem meeting scheduler by finding the earliest time slot that satisfies the required meeting duration. Here's the step-by-step breakdown of the code. 1. Sorting the time slots *, both slots 1 and slots 2 are sorted by their start times. This ensures that we can traverse through the lists in a sequential manner to find overlaps efficiently. 2. Pointer initialization * 2 pointers, I and j, are initialized at the start of their respective lists. These pointers help in iterating through the available time slots of both users. 3. Finding overlaps * the while loop continues as long as there are unprocessed slots in both lists. For each pair of slots, the potential overlap is calculated by taking the maximum of the start times, start, and the minimum of the end times, end. For checking duration *, if the overlap, end, start, is greater than or equal to the required duration, the function returns the earliest time interval, start plus duration. 5. Pointer movement * if the current slot in slots 1 ends earlier, the pointer I is moved forward, otherwise, the pointer j is advanced. This ensures that the algorithm progresses through the lists efficiently. 6. No overlap found * if no suitable time slot is found after traversing both lists, the function returns an empty list. The algorithm efficiently finds the solution using a two-pointer approach, with a time complexity of O, n log n plus m log m, where n and m are the lengths of slots 1 and slots 2, respectively, due to the sorting step. The traversal itself is O, n plus m. This makes the solution optimal for this problem, and it handles all edge cases, such as no overlap or insufficient duration, gracefully. Here, we begin by defining our Java class and method to find the minimum available duration where both participants can meet. The method accepts two 2D arrays, slots 1 and slots 2, representing the time slots of the two participants, and an integer duration indicating the meeting length. First, we sort both arrays by their start times to facilitate efficient comparison. This sorting ensures that the time slots are ordered sequentially, which is crucial for the two-pointer approach we'll use. Next, we initialize two pointers, I and j, to traverse through slots 1 and slots 2 respectively. Inside the loop, we calculate the overlap between the current time slots by determining the maximum of the two start times and the minimum of the two end times. This overlap represents the common time span available between the two slots. If the overlap is at least as long as the required duration, we return the start time of the overlap along with the end time, which is simply the start time plus the duration. If not, we move the pointer of the slot that ends earlier since it cannot contribute to further overlaps. If no suitable time slot is found during the traversal, the method reaches this point where it returns an empty list, indicating that no overlap of sufficient duration exists between the two sets of time slots. This ensures that the method handles all scenarios, including cases where no meeting time can be scheduled. By leveraging sorting and a two-pointer approach, the solution is both efficient and straightforward, making it well-suited for handling large input sizes while maintaining clarity and correctness. To solve this problem, we'll work through the first example, where we're given two lists of time slots and a required meeting duration of 8 minutes. The first step is to sort both lists of time slots. Here, slots 1 and slots 2 are already sorted, so we can move on to initializing two pointers, I and j, both set to 0. These pointers will help us iterate through slots 1 and slots 2 respectively. Now, we check the overlap between the first slots of both lists, slots 1, 0, which is 10, 50, and slots 2, 0, which is 0, 15. The overlap starts at the maximum of their start times, max, 10, 0, which is 10, and ends at the minimum of their end times, min, 50, 15, which is 15. This gives an overlap duration of 15 minus 10, or 5 minutes, which is less than the required 8 minutes. Since the overlap is insufficient, we move the pointer j to the next slot in slots 2, as slots 2, 0, ends earlier than slots 1, 0. Now, we evaluate the next pair of slots, slots 1, 0, which is still 10, 50, and slots 2, 1, which is 20, 50. The overlap starts at max, 10, 20, which is 20, and ends at min, 50, 50, which is 50. This gives an overlap duration of 50 minus 20, or 30 minutes. Since this is more than the required duration of 8 minutes, we can select the first 8 minutes of this overlap, starting from 20. The result is the interval, 20, 28, which we return as our output for this example. Moving on to the second example, we're given two lists of time slots where the intervals don't overlap. The required meeting duration is 5 minutes. As before, we start by sorting the lists, and in this case, they're already sorted. Slots 1 is 10, 20, 30, 40, and slots 2 is 50, 60, 70, 80. We initialize pointers I and j to 0 and begin by comparing the first slots, slots 1, 0, which is 10, 20, and slots 2, 0, which is 50, 60. The overlap calculation gives start equals max, 10, 50, which is 50, and end equals min, 20, 60, which is 20. Since the start time is greater than the end time, there's no overlap. We move the pointer I to the next slot in slots 1, as slots 1, 0, ends earlier. Next, we compare slots 1, 1, which is 30, 40, and slots 2, 0, which is still 50, 60. Again, calculating the overlap gives start equals max, 30, 50, which is 50, and end equals min, 40, 60, which is 40. Once more, the start time is greater than the end time, so there's no overlap. We move I again, but now there are no more slots left in slots 1, so we exit the loop and return an empty result, since no overlap meets the required duration. In the third example, we're given two lists of time slots where there's an edge case. The overlap between the slots matches the required duration exactly. The required meeting duration is 5 minutes. First, we sort the lists, and again, both are already sorted. Slots 1 is 10, 20, 30, 40, and slots 2 is 15, 25, 35, 45. We initialize pointers I and j to 0 and begin by comparing the first slots, slots 1, 0, which is 10, 20, and slots 2, 0, which is 15, 25. The overlap starts at max, 10, 15, which is 15, and ends at min, 20, 25, which is 20. This gives an overlap duration of 20 minus 15, or exactly 5 minutes, which matches the required duration. Since the overlap is sufficient, we return the interval, 15, 20, as the result. The output for this example is 15, 20, which is returned as the solution. This example demonstrates how the algorithm can handle edge cases where the overlap duration is an exact fit for the required meeting time. By iterating through the sorted time slots and checking overlaps systematically, the algorithm ensures an efficient solution to the problem, regardless of whether overlaps are partial, non-existent, or an exact match to the required duration. To analyze the time complexity of our solution, we start with the sorting step. Both input arrays, slots 1 and slots 2, are sorted by their start times. If we use Python's timsort algorithm, which is highly efficient, the time complexity for sorting slots 1 is O, m asterisk log m, and for slots 2 it is O, n asterisk log n, where m and n represent the lengths of the two arrays. The total complexity for sorting both arrays is therefore O, m asterisk log m, plus n asterisk log n. After sorting, we use a two-pointer technique to traverse the arrays. This traversal involves comparing time slots and advancing one pointer at a time. Since each pointer traverses its respective array at most once, the traversal step takes O, m plus n, time. Combining these two steps, the overall time complexity of the solution is O, m asterisk log m, plus n asterisk log n, as the sorting step dominates the traversal step for large inputs. Now, let's consider the space complexity of the solution. First, the input arrays slots 1 and slots 2 are provided as arguments to the function. Since we sort these arrays in place without creating additional copies, no extra space proportional to the input size is required for storage. Next, sorting with timsort uses O log m space 4 slots 1 and O log n space 4 slots 2 due to the recursive stack. Additionally, we use two integer pointers, I and j, to traverse the arrays, which require O1 space. Finally, the function returns either a single time slot of length 2 or an empty array, both of which use O1 space. Combining these factors, the overall space complexity of the solution is O log m plus log n, which is determined by the space required for sorting. The total space complexity of this solution is O log m plus log en, primarily due to the sorting step. Now, let's analyze the best, average, and worst-case scenarios for the algorithm. In the best case, the first overlapping time slot in the sorted arrays meets the required duration, allowing the traversal to terminate early. Here, the time complexity is dominated by sorting, resulting in O m asterisk log m plus n asterisk log n. In the average case, the function needs to traverse part of both arrays to find a valid slot, but the overall complexity still remains O m asterisk log m plus n asterisk log en. In the worst case, no overlapping time slots satisfy the required duration, so the function must traverse both arrays completely after sorting. Even in this scenario, the overall complexity remains O m asterisk log m plus n asterisk log n, making the algorithm efficient across all cases. Comparing this optimized solution to a naive approach highlights the efficiency gained through sorting and the two-pointer technique. A brute force method would involve checking every pair of time slots from slots 1 and slots 2, calculating overlaps for all combinations. This approach results in a time complexity of O m asterisk n, as every pair must be compared. In contrast, the optimized solution sorts the arrays first and then uses sequential traversal to check overlaps, reducing the time complexity to O m asterisk log m plus n asterisk log n. While the naive approach might use slightly less space, specifically O1, for extra storage, the optimized solution's O log m plus log en space for sorting is negligible compared to the significant reduction in computation time. This makes the optimized approach far superior for large inputs. Finally, let's summarize the mathematical proof of the algorithm's big O complexity. Sorting the slots 1 array requires O m asterisk log m, and sorting slots 2 takes O n asterisk log n. After sorting, the two-pointer traversal step compares a maximum of m plus n elements, resulting in a linear time complexity of O m plus n for this step. Combining these contributions, the total time complexity is O m asterisk log m plus n asterisk log n, as sorting dominates the traversal step for large inputs. For space complexity, sorting requires O log m space 4 slots 1 and O log n for slots 2, while the two-pointer traversal and result storage use only O1 additional space. Thus, the total space complexity is O log m plus log n. This balance of efficiency in both time and space makes the solution highly effective for the problem. Let's talk about some common mistakes that can occur while solving the meeting scheduler problem. First, not sorting the time slots is a frequent issue. This happens when developers assume the input slots are already sorted, but without sorting, you can't reliably identify overlapping intervals. Overlapping checks depend on the intervals being in order, so always ensure to sort both slots 1 and slots 2 by their start times before proceeding. Next, an incorrect approach to overlap checking is another pitfall. Some may assume an overlap exists just because one interval starts before another ends. However, this is only partially correct. For an overlap to truly exist, the start of one interval must be less than the end of the other and vice versa. Missing this precise condition can result in false positives. Lastly, relying on inefficient nested loops to check every pair of intervals is another mistake. While it might work for smaller inputs, this brute force approach becomes impractical for large datasets due to its n squared time complexity. Instead, using a two-pointer technique can reduce the complexity to n plus m, making the solution much more efficient. Now, let's explore additional challenges that can arise. Overlooking edge cases is a common mistake. For example, scenarios like completely disjoint intervals, intervals with zero length, or even empty inputs can break the algorithm if not handled carefully. Testing for these situations is essential to ensure the algorithm behaves correctly under all conditions. Another common issue is ignoring the minimum slot duration constraint. Developers may return results without verifying that the overlap satisfies the required duration. This leads to invalid outputs. To address this, always confirm that the overlap duration, calculated as n_overlap start_overlap, meets or exceeds the given minimum before returning a result. When approaching this problem in an interview, there are some key insights to keep in mind. Recognizing the pattern is critical, as this is a classic interval problem that tests your ability to sort and use the two-pointer technique effectively. Clearly communicating your approach is just as important. Make sure to explain how your solution addresses edge cases, such as disjoint intervals or overlaps that don't meet the minimum duration requirement. Interviewers may also ask you to compare the brute force method with the optimized two-pointer approach. Be prepared to discuss why sorting the intervals is acceptable despite its n log n complexity, and how it improves overall efficiency. Additionally, anticipate follow-up questions, like extending the solution to find all valid overlaps or adapting it to handle new constraints, such as finding the maximum overlap duration. This problem is closely related to several other interval-based problems that are worth exploring. For instance, problem 253, Meeting Rooms 2, involves determining the minimum number of meeting rooms required for a set of intervals. It's another example where managing overlapping intervals is key. Problem 56, Merge Intervals, focuses on combining overlapping intervals, which is foundational for mastering interval manipulation. Similarly, problem 986, Interval List Intersections, requires finding intersections between two lists of intervals, a direct variation that often relies on the same two-pointer technique. Lastly, problem 759, Employee Free Time, asks you to find free time intervals across multiple schedules, extending the concept of interval operations to identify gaps instead of overlaps. Finally, let's consider alternative approaches to solving this problem. The brute force method, which uses nested loops, is straightforward to implement but has a high time complexity of n*m, making it unsuitable for large inputs. The two-pointer technique is a faster alternative, reducing the complexity to n+m after sorting. This approach is efficient but requires both input lists to be sorted beforehand. Another option is the priority queue, or heap-based approach, which has a complexity of n log n plus m log m. This method is particularly useful for dynamically tracking overlapping intervals but can be harder to implement. Lastly, binary search can be an effective optimization if one list is much smaller than the other. Instead of scanning the larger list linearly, binary search can locate overlaps more efficiently, with a time complexity of m log n, where m is the size of the smaller list. Great job! We've successfully solved the number 1229 meeting scheduler problem, learning how sorting and two-pointer techniques can simplify interval-based challenges. Remember to practice similar problems to strengthen your skills. If you enjoyed this video, don't forget to like, subscribe, and share. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!